In fact, really, we need to start off with a memory map. I'm going to erase the CPU scheduling stuff.
You can get the red stuff too.
So this is a virtual memory system. We've been through this earlier in the week. We need to define things a little bit better, a little bit more accurately. Okay, so this is our virtual memory. Even on Linux, even on Windows, they're virtual memory systems. Linux, however, does not have the concept of virtual swap. So the top piece is virtual swap. It is not really there. It's a file in root there's a dot file there that's got 0 length to it. It does not exist. But we can, let me go to a different color. We can do reservations on swap. And then there's going to be a free piece of virtual swap. Anybody remember the command that I used yesterday to look at this whole map? When we turned miser up, on and off and stuff to reserve and unreserve? It was gross view, the SWP display. So that's the command that would show me, it lays it the other direction, but shows me my memory layout. The next piece then is my physical swap. And on physical swap, go to a different color here, we have reservations and then we have allocations. And then we have free. Now even though I'm laying these contiguous, that's not necessarily the way it is, it's just for simplicity putting together the map of memory. So the reservations were done on the malloc. The allocations were done when I touched the data. And this physical swap can be composed of several types of devices. Let me just put it over here. We can have what's called the raw device, any sort of raw partition, and /dev/swap is the default raw partition that everyone has. We can also put together physical swap with swap files. The advantage of a swap file is I don't have to take reboots. I can create, if I've got space on my file system, I can create a file and then do swapping into that, which allows me to dynamically react to a problem without having to take a reboot. Also, we'll talk a little bit about the fact that raw swaps, well, they're not really going into the volume manager as such, but they're going into the device driver, but they're using some of the threads that the kernel uses for buffer cache. But when I use swap files, they will show up as p-reads and p-writes and look like direct I/O. So I could have a system that has swap files on it, and it looks like I've got applications doing direct I/O, when in fact it's swapping going on. So you have to be a little bit careful about the fact that raw swaps show up differently than swap files in the SAR data. So when I'm looking at disk traffic, I don't know if the I/O traffic is coming from swapping or from file I/Os, unless I've looked at the swap statistics that the SAR gave me, the SAR-W, which we'll finish up probably about lunchtime looking at. Go ahead.
Always the swap use the p thread, the p read.
That's what it's been doing, but again, minor overlays, some of the stuff has changed. Earlier IRIX 6.5s, you could actually see physical swap show up as a b read and b write, but then they've shifted the code around and it doesn't look the same anymore. So I'm just saying you gotta be careful of it. That's why I look at *W to see if I actually have swapping going on. Now we're gonna come back to swap. The swap command is what put this all together for me. And the other option was NFS swap files. And these use buffer cache. They should show up with buff view. I was hoping that there was a buff view swap flag that would show me the swap pages that are actually out on swap, but I don't know of any command in IRIX to tell me what is physically out on swap. So if I've got swap full up, I don't have any command to tell me what's filling it up. But I have a trick that I do that I'm going to show you later using TS. So those are the three types of things that can make up my physical swap. Then I've got physical memory. And that's where we want to focus right now. Physical memory is also broken up. We also have the fact of reservations versus allocations, but I'm not going to focus on that right now. The main thing is, down at the bottom we have the kernel, and within the kernel is something called the kernel heap. The kernel heap is where the kernel keeps track of miscellaneous structures and stuff. That heap can grow and shrink and cause the kernel to grow and shrink. In fact, systems that are up for a month can have the kernel grow due to a memory leak or just the load on the system. And a reboot would show that it drops back down, and then the next month it may grow up again. So you got to kind of watch for that. Then above that, let me do it on this side. Up to NBUF is our file system buffer cache. Okay. Meanwhile, coming down, conceptually, that's conceptually, the way the displays like Grossview will show you, they just take all the user space and lump them together again. Okay, it is more of a scatter situation. There may be zones and stuff like that in terms of how I partition my memory and try to achieve different page sizes. And the coalesce daemon is doing garbage collection of these pages and stuff. So I'm just lumping them together into a single piece, saying that we've got a certain amount of space in memory being used by my user programs. And then in here is my free. And included in the free is something called inactive, also known as free C. All of this is my buffer cache, also referred to as chunk cache, because everything is chunked in blocks and stuff. Okay. Versus the page cache, which is all of memory. So that when I boot my system, every page on the system has a page header, and page cache essentially says that that memory page is sitting in memory. And I've got a page table describing where I can find it. Now, let's try a different color again. Black. Within my cache, I then have my metadata, or FSCTL data. That was the inodes and directory block information. We had settings, I'm just going to put them here, to control, actually when I push, this is able to go up and down. Let me put it this way. So there is a ceiling and a floor to how far I can let that thing grow and shrink. And yesterday, I think it was, we looked at Fido.Inger and saw a couple of settings that have been changed. Anybody remember what they were for our name cache? We had NC size, And when I pushed down, it was called min buff map. These were sys-tuned parameters. Okay. Above that then was my dirty data. What's dirty data?
Hasn't been written out to disk yet.
And what happens if I don't write it to disk?
You lose it.
Well, not necessarily. I lose it when? When we power it off.
Crash or.
If I get an interruption. It could sit in cache for days and weeks, and as long as there's no service interruption, I don't really care if it goes to disk. So I have seen stuff sit in cache for days. So it takes the service interruption to actually cause the loss. And that's what we talked about yesterday, where with journaling, it might be metadata that I have in memory that hasn't flushed the disk yet. Remember, the flush rate was BFS underscore sync R to say how often do I flush it. The slide that I'm on right now is talking about the dirty data. So what does the slide call it? Instead of dirty data, what's the name? Delayed write. Okay. So you can also call this delayed write. Funny story for me, for years I called this lazy sectorization. You're pushing it through the kernel and letting the kernel sectorize the data, because when it gets out to disk, it has to be at least 5 12-byte chunks, because that's the size of a sector on disk. I can't write a 9-byte piece out to disk and let it understand it. Windows calls this, instead of delayed writes, they call it lazy writes. You get into their SAR, their perfmon, and it's called a lazy write. So delayed write data is data that I'm stuffing into the kernel and then let the kernel worry about it. It's his problem, not mine. Okay? Now what command actually manages that dirty data? Up on the slide. We also call this flushing the dirty data. BD flush is the piece of the kernel that maintains this dirty data. Now, if I'm on a system where I'm reading more than writing, I don't care about the dirty data. But if I'm writing more than reading, then I do. Also, if I see memory maps and this is getting big, then I do. So again, if it's not that situation, a web server, I would expect to have more reads than writes, and I would not expect BD flush to be relevant there. Okay, not every situation has dirty data problems. So BD flush is the command that's doing this. And BD flush controls how much memory footprint this delay write area is going to have. Okay. If I stuff a whole bunch of data into the kernel and say don't flush it, it could grow rather big. But eventually I need to move it from dirty to what we call clean. And clean could be busy, or after 5 seconds. It varies from release to release, anywhere from 5 to 100 seconds. Now, I'm going to test for that today. It will then move it from clean to inactive. So as I write data, I stuff it into memory. All my reads and writes. Remember yesterday we said by default all my libraries are going through buffer cache. I have to ask to bypass it. We haven't looked at SAR-B yet for the week to see if we've actually done any physical I/O yet. So everything that we're doing is going through this buffer cache as a resource. So if I write, that cache piece is going to be a dirty buffer that has a DW marked on it with buffview, for example. We saw some of that yesterday. And then BD flush wakes up and says, okay, let's take that dirty data, sync it, flush it to disk, and mark it as clean. Okay, and once it's clean, I know that if I take an interruption, I've got it on disk. Now, I don't want clean to get too big. So, if I have a large NBUF, I don't want to have a lot of N buffs to have to check to look for data every time. So after a given time interval, you'll say that clean data has not been busy for 100 seconds, for example. So I will then move it from clean to inactive. Now, if the users need memory, the first thing that should go should be the inactive, stuff that hasn't been used in a long time. Or, depending upon your overlay level, it may just suddenly release it saying, let's just throw it away. So we're going to load up the system and take a look at data moving from dirty to clean, clean to inactive, and see how long it takes to do those things and stuff. So with BD flush controlling the dirty piece, starting off this whole process, it has parameters to control when do I flush this stuff to disk. And BD flush at the command line level is called sync. And some of us used to remember the days we do a sync during our shutdown to make sure that everything in cache had a chance to flush to disk. The trouble with sync is it's asynchronous. You get your prompt back before the sync is done. We also had days where the dirty data would get so big that the disk drives couldn't keep up with it, and we'd have a sync occur before our prior sync was done. So if I've got a 64 gig machine and I let dirty data grow to 38 gig and my disk drive's 5 megabytes per second, I'm in trouble. We don't want to let it get that far. We'd like to keep ahead of the dirty data. So BD flush has its own process of flushing. Now we can do a sync command, or applications can do a sync. There's also a system call, for example, fsync, that is actually synchronous. You don't return from that call until the entire flush is done. Again, remember, if I'm not writing data, if it's not dirty data as a problem on my system, I'm not going to worry about any of this. Only when I see it as a problem. And I see it as a problem because the amount of memory holding dirty data is high. So BD flush has parameters to control it. And one of them is called, well, there's one not marked here right now, BD flush interval. So BD flush underscore interval, by default, it's every second. How often do I wake BD flush up? For Ccahe people, we're doing every 2 minutes. They do it every second. So BD flush interval is saying how often do I wake up and sync my data, flush my data to disk. The next one that's mentioned here is something called BD flush R. BD flush R says what ratio do I look at? In my prior example, if I filled up my buffer cache with a lot of dirty data and my disk drives couldn't keep up, I would not want to try to evaluate 38 gig of dirty data every second. What do we do in the Ccahe world? Put you on the spot. When we started flushing to slow down the flushing problems, we created LD cache and called something called trickle sync. Trickle sync is a concept of basically saying let's keep ahead of the whole story. IRIX has a trickle sync too. That's what this is. BD flush R is saying what ratio of my buffers do I look at? Now with Unicode, we could trickle sync based upon age or ratio. Most people synced upon age. Okay, but there was with LD cache the ability to flush based upon number of buffers dirty. So with BD flush R, it's basically N buff divided by BD flush R. That says how many of these buffers do I look at? Because I don't want to look at them all at once. So if BD flush R is set to a 1, how many buffers do I look at? If BD flush R is set to 1, how many buffers do we look at? All of them. Okay. As I make BD flush R larger, I'm looking at less buffers and therefore trickle sinking more. So as BD flush R is getting larger, I'm going more and more trickle sink. In other words, I don't want to handle a 38 gig dirty delayed write buffer in memory because I've set nbuf to 600,000 and now I suck up all this dirty data and my disk drives can't keep up with it. I don't want to start the next sync before my prior sync is done. Okay, I don't want to queue up the next stuff until I know that I can handle the older stuff. In 6.4 they had this problem. There was a command, shake D, that would wake up and use the time of the last shake to do the next shake. So if I got a bad load on the system, I'd get a long shake and then it'd put me to sleep for a long time and I wouldn't know what to do. By the time I woke up again, everything was out of control. And this is one thing that IRIX needs a little bit better control of, is different file systems need different flushing intervals. This tape isn't planned for anybody for us, but LD cache is something that IRIX desperately needs because I can segregate my file systems. You know what LD cache does for us, Chad? I've been at a site where you drop LD cache and the performance gets worse. You put LD cache on and it's better. But what they're doing is isolating a scientific application from taking the entire buffer cache pool. And you're only allowed a certain number of buffers. So the people in the home directory don't get impacted by buffer consumption from the scientific code. We're partitioning our buffer cache and isolating abuse to a certain set of buffers. So the site would put on LD cache and the cache ratios were terrible, but the response was good. Okay? Then they'd take it off, response was terrible, but the ratios were good. And that's because the ratio went bad in the file system that the application was abusing in. And it isolated me interactively and my ratio was good. It protected me from the file system buffer cache abuse that scientific code did. So again, with IRIX, the bigger the cache, the more I can abuse it, the more I can hold. And there's no prevention on a per file system basis. So some code comes into Miser, grabs all the buffers. I'm in a different file system, but it does me no good because I can't get through buffer cache. Whereas with LD cache, I could have.
Are there any plans to implement LD cache
No.
in IRIX?
No. LD cache. Page size control, and that was also handy. I'll come back to that story a little bit later. So there was this concept of trickle sync, and basically I'm trying to address for Janice, and she's going to be teaching it too. The concept of trickle sync is there in IRIX. As I increase BD flush R, I'm trickle syncing more. I'm taking off less of the cache. So as I increase nbuf, I should be increasing BD flush R. I like to keep them at the same ratio. Now BD flush R by default was 5, so the default is 20%. It's set to a 5. It comes out to be 20%. So I'm going to evaluate 20% of my nbufs every second. Now when I evaluate them, I've got to come up with a standard, and that is the next parameter called AutoUp. And AutoUp says, what is the age of the data before I flush it off to disk? And that is a default of should be 10 seconds. Now I'm going to leave all these alone if I'm a web server reading more than writing. And keep in mind, in the database market, this is controlling the metadata, but not the actual data. Okay, so my meta index and stuff like that will be in buffer cache because it is in the file system. And therefore these can influence if I've got lots of writes going on to my metadata. And you've just got to be able to decide, am I writing more than reading or reading more than writing? And we've seen several metrics that give us that. We're going to see some more today. Because we're going to look at L reads and L writes, P reads and P writes, and B reads and B writes. That's where we're going next, is to actually look at those numbers. Now, AutoUp, depending upon your release, also influenced how quickly I go from dirty to clean, but also clean to inactive. So it was saying, for example, it was 10. So if it was in this delayed write area for 10 seconds, AutoUp would say, after 10 seconds, flush it, and then mark it clean. So we get a 10-second wait, approximately. Let's see what auto up is on our system. Is it 10 seconds or 5 seconds? Or 10 seconds. Now if I had that scenario of a read, read, write, I may have to cancel the prior write because it's still in cache. Why flush it to disk? So in scenarios like that, particularly like random I/O, I may get back to the data quick enough, change it before it's flushed to disk. And then I don't have to take the disk overhead of bringing back in just to change it. So some sites may slow down auto up in order to give the data longer chance to stay in memory before I destroy it. For example, on a send mail spam attack, it might be helpful for me to slow down auto up so that I don't have to thrash a disk to bring it back in, assuming I got memory space to hold all this stuff. So auto up says after 10 seconds, it's going to go from dirty to clean, and depending upon your release, in some of the releases, it then controlled 100 seconds to flush it from clean to inactive. That was earlier overlays. It then became about 10 seconds or 5 seconds. It varies depending upon your release. And whether auto up actually still controls that depends upon your overlay. So you don't want to get that detailed about it. So that's what controls the size of this dirty delayed write area. Is BD flush R, and the key parameters that control it are how often do I wake up to do my syncs, what percentage of the buffer should I look at, and how old do they have to be before I flush them. And if it's getting out of control and getting too big and I don't have the memory to do that, I may want to wake BD flush up more often, or I may want to properly size my requests, or I may want to speed auto up, shorten it up so that I can keep ahead of the story. Now there was one other parameter mentioned there. I'm going to put them here. DW cluster and CW cluster. When I do the sync, when I do the flush, that is the size of the flush. I'm going to try to cluster my pages together. Now if I can't make a cluster, I'm still going to do the flush. But I'm going to try to group these things together, and that's the request size story. If I'm striping, I'd like to up my DW cluster. I'd like my DW cluster so that it's coming out of the back end of buffer cache. Whenever I do my writes, I'd like to size that write to fit the geometry of my file system, what the file system considers to be a friendly I/O request. And CW clusters if I'm pushing it across networks. So CW cluster would be to NFS, and then I'd want to know the maximum transmission unit size and the read and write record size for NFS as it was mounted. So those control the size of my writes. So what do we got now? We had 2 systune parameters there, 3, 4, 5, 6. May as well go on over here. 7, 8, all at once. We also had 9. There are a couple other parameters to talk about here, just to get them out of the way now while we're right on the subject. Getting away from the dirty delayed write story. The clean piece, its size. If I increase nbuff, clean can also grow to nbuff. So nbuff is my ceiling. When I push down, there's a command called shake D. Actually, it's a kernel daemon. I shouldn't say it's a command. Shake D's job is to push the kernel down whenever I start running out of memory. If the users want the memory, I'm going to push the kernel down. If the users don't want the memory, that clean data can stay in there, except it's going to eventually go to free C, and then the clean will drop down anyways. And again, these behaviors change in every overlay. So when I shake the kernel down, because I'm running out of memory, and basically VHAND has told Shake D, wake up and push the kernel down, manage the cache for me. The floor for that is called min file pages. Min file pages is my floor. So if I'm on an NFS server and I've got lots of memory, I've loaded up memory as much as possible and it's not being used, I can increase nbuf and increase min file pages and increase NC size and increase min buff mem, and that allows everything to have more breathing room in memory for key metadata inodes for an NFS server and the actual data that's actively being used through that NFS server. So all these things are raising the ability of me to use memory for these particular resources. So my ceiling is nbuf and NC size. My floor is min file pages and min free pages. I'm sorry, min buff mem. So that's number 10. Now, Shake D also has another parameter that controls this. How much space am I going to keep between my users and my cache? So Shake D is waking up and trying to push the kernel down. It's going to push the kernel down based upon min file pages or min buff mem, but it's also going to have another stopping point here, and it'll say once I hit min free pages, stop. So this one is min free pages. So min free pages is saying how much memory do I keep between my users and my cache. Now some sites have upped min free pages, and that can cause swapping. VHAND is also working in here. Remember when I said at the beginning of the week, parameters can interact? These are all the parameters that have interactions. It's hard to change one of them at a time and see the effect because there's so much dependency between them. So also in here is VHAND. Now VHAND will stop at 100 megabyte. It will not try to recover more than 100 megabyte of memory. But if I've loaded up my system and I keep allocating pages, VHAND is going to have to start stealing those pages and pushing them out to swap. So VHAND is what's turning the memory shortage problem into an I/O problem. Now hopefully Shake D is going to prevent that from happening by keeping the kernel down as much as possible. But eventually we push the kernel down as much as possible. Now we've got to start getting with VHAND, turning that memory shortage problem into an I/O problem. So Shake D has to wake up first to do its work and keep the kernel small. And if it is as small as possible, then VHAND wakes up and says, do I have 100 megabyte available? Okay, don't need to worry about anything. If I'm running out of 100 megabyte, then I better start worrying about things. Now on a 64 gig origin, VHAND and 100 megabyte, it doesn't look like much. But it is turning my memory pressure into an I/O problem as programs keep growing, and I have to push that stuff out to swap. So VHAND has a couple of parameters to it. One was the RSS hog frac, which is saying what percentage of memory do I try to keep free. And then the other one was gpages high and gpage low. Okay, so these are actually going to control how much room VHAND tries to keep. So min free page is a Shake D trying to keep things open, and VHAND has RSS hog frac, gpage high, gpage low. I'm going to save that for after break. So that was 10, 11, 12, 13 systune parameters in one drawing, because they all influence my memory map. Sorry it's messy, it comes out different every time. But think of each of these pieces as a resource, and I can't control the kernel in the heap, but I can control the metadata, the dirty data, the clean data, the inactive data, and the free. And the users in the load determine the user footprint. And when I start running out of memory, things go out to swap and start becoming allocations out on swap. I'd like to take a break here in a few minutes, but so in the workbook we were just talking about the dirty portion of that memory map, but I really needed to put the whole story together, so to speak, on how these things fight for resources. And by the way, Linux has a lot of the same similarities. It's not identical, but it grows and shrinks and has controls for each of the different pieces. So on I/O markets like mail servers, news servers, even web servers, having as much memory as possible and upping these to take advantage of that memory is good. There's nothing wrong with seeing a 38 gig kernel if the purpose of my system is to do I/O. Okay? And all of this is for latency, not bandwidth, remember. This is to get the data quickly. So if I'm in VI, that's a latency situation. I want to get to that page and change my characters. I want to do global searches and stuff. That's latency, not bandwidth. Whereas in the video market, that is the other extreme, where it's pure bandwidth, as well as the scientific market. So files, when we write to a file, whether it's a print or whatever, a write statement, we have to write into the dirty portion of the data, and the data is kept in physical memory for auto uptime. Now it's actually in memory beyond auto uptime, but we then flush it to disk, but it's still in memory for a little bit longer. In fact, in some cases up to 100 seconds or 10 times auto up. So auto up is basically controlling the age of the pages before they're flushed, and then BD flush R says how many do I look at. If I'm upping nbuff, I'd like to keep BD flush R, that ratio, something tolerable, so I don't try to look at more buffers than I can push to my file system. And when I do the push, there's DW cluster. By the way, clustering is counted with OS view on display 5. Under the file system buffer cache area, we talked about delayed reservations there. Here's my clustering metrics. How many clusters did I try? How many did I actually cluster? I don't have any write data going on in the system right now, so it's not doing anything. So that's what this drawing is trying to show. However, the drawing is a little bit different than it should be. That's a better drawing. And some of the stuff has changed in terms of whether we count inactive cache within the min free and the nbuff. So this was more like a 6.5 vanilla when I drew this drawing. And now nbuff is actually, we're going to find out in 6.5.10 how far nbuff can go, and then how far min free pages can go to keep things free. And min file pages, again, was the floor. So this is just a simpler drawing from what I have on the board. And we've talked about buff view. I'll come back to it as needed, but there are a lot of metrics up at the top that basically I tell people, look at the man page to find out more specifics. The main one was the number of buffers, how many of them are system, how many of them are data, how many of them are empty, and then being able to look at the busy and also the fact that things are juggling in the list. Those are the things that we care about. And then we looked at the buffer flags. We've already been looking at busy. The one that I wish worked was the one for swap, the SWP display. But that never shows me any of the pages that are out on swap. Because one thing I want to know is if my swap's allocated, what is it that's allocated swap? So the F option just allows me to look at different types of buffers. So we've got to look at SAR-B data, and we have to look at a memory map. And 10-10 is just trying to draw the drawing that I've got up here. I'm going to have to talk about a story on that. So let's try something here. OS view, capital D, RMEM, RMMC, RMM strip mode, RMMC strip mode, SWP, SWP strip. So those are the best. PCP has these same sorts of displays, but not as easily built. But those are the 5 key or 3 key displays, both in speedometer and then in strip mode, to describe the memory map that we're talking about. So if people are running out of memory, this is the interesting display. This is the RMEM display, this is the RMMC display. The difference is whether free C is counted. Free C was the inactive portion of the cache. Data that was clean and is no longer used. It's rather large here. We simply do not see it here, it's not reported. If I run out of memory, that should be the first thing that I release. I have those same 2 displays then in strip mode. So in strip mode, I can still see across time. Looks like there's some workload growing right now. And what I'm going to try to do is push the kernel down and see what happens. The last 2 displays are kind of hard for us because I got too much virtual swap here. But here's my physical memory with the reservation out of it. I already see some yellow showing that I've got some reservations going on out on swap. Okay, so this is showing the swap portion, the top portion of the chart. So the RMEM and RMMC are showing this piece, and SWP is showing this piece. So I've already got some swap allocations going on. In fact, there's some pages that are out on swap, and I've got memory available, but I still got stuff out on swap. Now, how could that happen?
Reserved memory.
Well, this is beyond reservations, but what I'm looking for is the fact that we could have had a memory event that squeezed things out on swap. Nothing's going to bring it back in unless I demand it. So it's entirely possible to have memory available and things still out on swap. Let's just find out. Swap-ln shows that there is allocations, not too much, but there is allocation going on out there. Oh, not enough space. So it looks like I was not able to delete, boy, not much. A little less than a meg that I didn't have room for. Now that's kind of interesting. It should have been able to move it from that device to the other swap.
And they got rid of that virtual swap, so
Yeah.
at least your strip will look better.
True. Did it show that yet? It caught the change there. So now my swap display is much different. Showing my reservations. Note that there's no red in here, so all my memory's been used. Remember, Miser's running, and Miser took reservations from me too, and that's causing other stuff to sit out on swap. Now these 4 colors here, I basically tell people, look at the man page, but there are differences between reservations and allocations. These are the actual allocations. The green here is the allocations that are out there. But I could have had a memory event a while ago and had allocations move out to swap, and the only way I could bring it back in was what I attempted there with the swap command. Anyways, I'm going to do a ITC init.d swap start now and change it back. Okay. So now I have this huge virtual swap again. Now, before we go on, what's buff view show? So Buffy shows I got 100,000 buffers, 30,000 are metadata, 3,800 are for data, and I do have inactive. There's 36,930 showing as inactive. Now with the F option, I can look at what those things are. I'm just going to try that SWP one and see if it shows anything. I didn't expect it to, but I wish it would. No. So again, if I want to look at the inactive portion, there's another flag for that. There's 36,000 of those. Do an F, and it's INA. Find out. Unknown flag. INACT. Now they won't have names to them. Taking a while. By the way, there's one other piece I should tell you. I have a tool to get the vnode number back to the file name. I've got a Perl script that will cross-reference that vnode number and tell me what process and what file it is. Looks like it's just sitting there. It's called SVQ. I can do an svq.perl. It's a Perl script. Oops. And it is running iCrash and then going through all the open file tables. So if I've got something sitting there in my BuffView report, this one I picked was SA file. I probably know who that is. But maybe there's something else that I was interested in looking at. I can find out who was actually using it. So right now it's going through all the buffer header chain and figuring out what's going on with everything. It's running iCrash to do this. And that BuffView never did come back on a per inactive basis.
How far back on iCrash will that Perl script work?
It's on the current system. So if the system is changing, it's just when it took this snap right now.
No, I'm talking about, will it work for iCrash 655, 650?
All 6.5s that I'm aware
But it
of,
won't go 6.2, right?
I don't think so.
Okay.
Unless they, I don't know if they've changed formats or not. It hasn't been tried on 6.2. So it basically went through that buffer header chain so I can get new data or reload from the system, list mounted file systems, or here's my vnode lookup by vnode number. So that's what I'm going to try here. I think I have to be in hex, so I have to have the 0x in front of it because it was not over here. Okay, so it now went through there and found this information for that particular vnode number. So I got the inode number, the size, the file system that it's in, that sort of information. There was also a file list for specific process ID. I can dump it into a raw file. Let's see PID, let's find the PID that's interesting. Well, there, finally I got the inactive. Okay. Now it doesn't tell me much here. This was it's just marking them as unknown, null device and everything, but this is the buffer header number. And I don't pay any attention to offset. The age, these all look pretty old compared to the current tick, so they've been there for a while. I wish that BuffView would actually do the arithmetic between the age that's on the file buffer and the current timestamp that I have. Okay. I need to be able to break out of that right now. So let's see, do we still have that inactive cache? It is still there. Let me get out of this.
So if you did a sync right now, that would start flushing that out.
No, sync is only for dirty data, and we have no dirty data visible. But that's the point right now, is what can we do? Can we push that out of the way? So I'm just going to give it a try here. With systune, these parameters, except for nbuff, are all dynamic parameters that can be changed without a reboot. Oops, I better reboot first. And they're all in the paging group. It's the same group. There's CW cluster. Ccahe also had his own interval. Min buff man, min free pages, min file pages, auto up DW cluster, RSS hog frac, BFS sync R, BD flush interval, BD flush R, G pages high, G pages low. The max parameters I mentioned are useful if you are going to stripe swap. These are the max parameters I mentioned yesterday that control the size of the request coming from the kernel to the swap device. So what I'm going to try here is min free pages and see whether that's going to affect the inactive portion of my cache. I'm going to drop that down. Actually, I probably want to make it real big. Let's just see what happens. So I better write where I am now first. Let's go 300 and see what it does. Do I really want to change? Yes. Okay. Of course, it didn't do anything. Now let's try min underscore free underscore pages. Let's go to a big number. We've got 100,000 here. Let's just try 60,000. Okay. And no change. So min free pages was not counting that. Like I had up there, it was achieving between free and clean. Let's go a little bit bigger, just see what's going to happen here. Okay, it's still real big.
Yeah, there he goes.
Ooh. So it's not affecting this, but it is affecting the cache portion, so it's behaving the way I drew it. Okay, so I am now pushing the kernel down, and buff view would have shown everything that just got squeezed out. So min free pages was not counting the inactive portion, but counting the cache portion, and it just pushed the cache portion down. And that's shape D, shaking the kernel down. So I now have a much smaller kernel, and buff view would show a different content with everything that just got squeezed out of buffer cache. I'm going to set it back to where it was, 12,800. So if a customer complains that their cache is too big, that's the way you can squeeze it down. Okay? And you're just basically pushing everything out of cache. Now I can set it back up, and I don't have a load to fill it up yet. Not an I/O load going on. 4 with 3s.
The threes.
Yep. Let's see if we can see that now. So here is where we actually had the squeeze down. Note that it basically squeezed everything out. It looks like some of it did go inactive, and inactive got a little bit bigger than it was before. So it squeezed it from the clean to the inactive. But I was not able to push the inactive down. The inactive actually got larger.
There we go.
So now he's running a load, and 3 is writing more than reading. Remember we saw that? So there goes my dirty data. So he's fired off an I/O load. Now I've got nbuff set real high, so as long as the users don't need it, the only thing that's going to keep this free is my min free pages. NBluff will go all the way this unless I hit end free pages, and then I'm gonna have to start moving stuff from clean to inactive, and the inactive may actually start growing. Note now, about 10 seconds later, the stuff that was dirty started going into clean. Okay, so we got a whole bunch of writes, and then the writes actually started flushing, and the clean went from small to large. So all that dirty data has now been flushed into clean. Now the question is, how long does it stay clean before it goes inactive? In 659, it suddenly would drop periodically. So he's just loaded up buffer cache. Pop up buff view and see what the files are in there. I would expect them to be those temp files or TST RFE files.
Temp dot, capital Fs, dots.
Now the users aren't asking for this. It looks like I'm getting a little bit more cache growth there. There was a little bit of writes going on in here, and then the writes are actually going to clean. That's causing everything to grow. So at this point now, we're going to start running into a contention between these two. And it looks like the yellow is starting, the yellow should be what should start to release next. Right now the yellow has not changed much. And that's the question is, when I want that yellow, can the workload take it from me, or am I going to start pushing the kernel down? So I'm playing a battle between these different resources, abusing one and see who gives up and who wins.
So on the second graph, the green area, that is the real max free,
Right.
or min free right there.
That is completely unused. The B-hand is trying to achieve that.
Question, why would you want to have that? I know, in one instances, would the system go in and use that space up? Or why would you want to leave a space in there?
You always need some space to resolve deadlocks, so that you got breathing room to get stuff out of memory before you hit a deadlock situation where you just can't keep up with things. So you always want to have some free. Now the older machines, 25% is what they tried to keep free, but that was 96 meg, 128 meg machines. Once you get past 4 gig, it stops at 100 megabyte. What got there, my clean just got released. Okay. Is the workload still running, by the way?
No. It's like it finished.
So once the workload finished, the data that was in the cache got released rather quickly, and my cache dropped back down again. And my inactive was not affected by any of that event. Are there any code 3s running at all now?
Just starting some more up.
Sure. He's saving me the window. Now the other question I still didn't see though is when it got this close, whether I actually can still recover that memory with the way the system's configured right now. There we see the next load start off. What I want to know is if I fire off these code 4s, are they going to release the yellow as they should? We just hit the bug. That is a bug. We just ran out of memory, and all the displays are going to show that as a super big number. Remember when I was looking at data yesterday and had those real spikes? This is how grocery shows it. So I can't tell if that inactive was actually released because my display just wiped out on it. And that means that I'm swapping more than likely. And we can see here that I did push my kernel down now. So NBluff was showing me my ceiling. Now if I throw code 3s off, code 4 should win over code 3s. Code 3 should not be able to push the kernel up unless I raise min file pages. So right here we've got the two battling against each other. I've got write data going into clean, and then I can see the clean data being squeezed out as the two of them are breathing. So I'm writing into here, then squeezing out into here. That one's growing, and then that one starts shrinking. But I can't see the inactive. That's what I wish I could see right now. It completely wiped out right there. I had one site that actually thought that they had plenty of memory at this point, and in fact they were completely out. SAR-W at this point. Not a whole lot of swapping.
I'm just throwing a bunch of PIO.
It's occasional trickle. There is a physical I/O showing.
Yeah. Saturated.
SAR 1/15. So all that I/O showing is file system buffer cache contention right now, 13% weight I/O. That would be for your code 3s more than likely. DSEF, grep for buff. Oops, I'm only picking up buff view. Oh, I forgot the L. I only picked up buff view.
Well, it's BIO, isn't it?
Are they hanging on BIO? That's what I was checking. There they are. Codes, all the code 3s are sitting there on the BIO lock. Okay. And SAR-Q would show them how many? 1, 2, 3, 4, 5, 6, 7. So I've got about 6 on the weight IO queue, it looks like, 6 to 8. So those are the processes that are in that weight IO state. My CPUs are oversubscribed at this point as well, so my CPU utilization should be pretty good, except that we've got that weight I/O of things that are sitting there waiting to get to the CPU. Now, this display that we had here is also the SAR capital R option. And there's the number that has gone and wrapped. That's what's causing everything. PCP will get the same number, so will OS view, so will SPV. So here's my physical memory, the size of my kernel, the user. I lost my header. Looks like it's starting to free up now. Let me close and reopen. Not quite there yet. So the display that we've just been looking at is available with SAR ASCII. There's my physical memory. How big is the kernel? How big is the user space? Metadata, dirty data, clean data, and inactive data. And then the number that has gone negative instead of saying 0 is the empty. So that should be 0. When that is bigger than physmem, it's wrapped. Instead of showing negative, it's gone super big.
Buff view swapping.
Buff view should show some contention going on. And again, the thing that I'm looking for is things toggling in the list as they're thrashing or fighting, and you can see lots of activity. Now, when I was on that news server, I actually saw the metadata and the data thrashing, where the metadata that it needed to do its work was so huge, because it hadn't gotten rid of all the old news articles. It had this huge database of inodes, and then it toggled to this history file. And you see the two of them thrash back and forth. But I do still have empty buffers, but the users aren't allowing me to get to those buffers. I have contention. So I got 857 for data, 7,495 for my metadata, 48,000 that are empty, and it's showing 43,000 that are inactive right now. I think it's probably a good time for a break. I wanted to take a break about 15 minutes ago.
Okay.
So let's pause and take a break here.
Because the number of, excuse me, well, the number of